All right, it's 10 o'clock. We'll get started. So reminder that your test is on Monday, this Monday. What we go over today will not be on the test. And it's like test two. It'll open up at 12 a.m. on Monday. You'll have 11:59 p.m. to finish it. For the test, what I'm going to do, since it's very problem based, I will open up a Turnitin to for you to submit any work that you do, and a chance to possibly get partial credit in that if you set up the problem right, you might still get something even if you got the answer totally wrong. So I'm going to create a folder for that. Yes, homework will be due Monday because we had class on Monday. And since they're always due a week afterwards, after we do the class. So the homework that's due this Monday does relate directly to the test. So it's a way of studying for the test. All right, so with that out of the way, and it's, oh yeah, then the test is going to be like open note again. Make your equation sheets, get ready to go, all that good stuff. But with that, is there any other questions about the test before we move on to talking about light for today? All right, so let's talk about light. We ended on this slide on Wednesday, where we just introduced light and how it has a magnetic component and electrical component. So here I'm showing what is called the electromagnetic spectrum. And this is just all the different types of light that's around you every single day. And some things to look at on this. Here we have frequency. Remember, frequency is just how many times a wave passes a certain point in a given time. And it has the units of a hertz. And we also have wavelength, which is just the distance between waves from peak to peak. And we also have energy here, from low energy to high energy. And so when you probably think about light, you only think about probably visible light, all these different colors. But technically, everything on here is a type of light. You just can't see it. You have ultraviolet, X-ray, gamma, infrared, microwave, radio. So all different types of light. Now, one thing I like to point out is this microwave here. Microwaves are generally low energy, but it's always funny when I see people talk about, how microwaves are bad for you. Well, they're very low energy, so they're not really that bad for you. And cell phones are even lower energy than the microwave. So having like a cell phone up to your head isn't that much worse when it's talking about energy than the TV waves that are going through you right now, or the FM and AM waves going through your body right now. So don't need to worry too much about that in terms of energy. But I just want us to get a little practice of looking at the electromagnetic spectrum, getting used to it. So here, 4 different types of waves, 4 different types of electromagnetic radiation, rather, if I'm going to be more specific. Just list these from low to high wavelength and then low to high energy. So take a minute, familiarize yourself with the electromagnetic spectrum, and get this list. And yeah, I'll give it the answer in about a minute or so. Right, so if we look at the electromagnetic spectrum and we're just seeing, okay, from low to high wavelength, how does this go? Well, the lowest wavelength would be UV. So these negative numbers, right? This is units of meters. And so the negative exponents mean very small. So UV has the smallest wavelength, followed by IR, infrared, then microwave, then radio. And if we are looking from low to high energy, it's just reverse. So low energy is over here. So radio has the lowest energy, microwave, infrared, UV radiation. So some trends from here. The smaller the wavelength, the higher the energy, the higher the frequency, which makes sense. So again, let's imagine that you're standing at a point, yay, and you can see all this type of electromagnetic energy. So if a wave looks like this, and it's heading right for you, you're going to get hit by this wave a lot in very short succession. And so this has a very small wavelength, because wavelength is peak to peak. It has a very high frequency because it's going to hit you a lot in a short amount of time. Therefore, it's high energy. Compare this with a wave that looks like this. So for this, right, the wavelength is very big, which means that you're going to get hit a lot less often because it just takes a long time for one of these waves to come and hit you. Therefore, that's why it's low energy. So that's kind of the way I think about that in terms of like visualizing it. But that's how all three of these are really connected. But is there any questions about the electromagnetic spectrum to begin with? All right. So question 2, looks like we do have a question. The DCBA was energy. DCBA is low to high wavelength. Energy is ABCD, low to high energy. All right, so let's do a little bit of math then. So we have an equation that can relate frequency of wavelength. Remember this nu, or V, is frequency. Lambda, or this weird kind of triangle, that's wavelength. C is speed of light. So I want us to get to use these variables. So I'll do A for us. Calculate the wavelength or frequency of electromagnetic radiation. So here I have 100.2 megahertz. So I hope you remember what your prefixes are for that we learned all the way back in like week 2. Mega equals times 10 to the 6. I don't know why I did big X there. Should be times 10 to the 6, right? So 100.2 megahertz is 100.2 times 10 to the 6 hertz. And that is a frequency. Anytime you see hertz, that's a frequency. So if we look here, our frequency is 100.2 times 10 to the 6 equals our speed of light. You can just do 3.0 times 10 to the 8. Makes things easier. 0.0 times 10 to the 8 divided by our wavelength. So different ways to solve this. Probably the easiest to do on a calculator base is just multiply each side by the wavelength. So you get 100.2 times 10 to the 6 lambda equals 3.8 times 10 to the 8. Divide each side by 100.2 times 10 to the 6. Let me get my calculator out. 100.2 times 10 to the 6 divided by, so this will be 3.0 times 10 to the power 8. Divide those two. 2.99 lambda equals 2.994. All right, and now we have to figure out what is the units. So speed of light is meters divided by seconds. And we have this hertz, and hertz has a weird unit of inverse seconds, or 1 divided by seconds, because it's basically, frequency is how many times a wave will pass a point in a given amount of time. So what this 100.2 megahertz says is that 100.2 times 10 to the 6 waves will hit the same point in 1 second. So it'll pass through that point every 1 second. And so when we have these two, so we have meters per second divided by 1 divided by second. And if you remember, when you have your fraction divided by a fraction, you can just take this and you move it to the top. But when you do that, you flip over your second fraction. So this is meters divided by second multiplied by seconds over 1. Seconds cancel out. And that is meters. So the wavelength of a radio wave is roughly 3 meters. What is on the other side of the equal by that m? That's times 10 to the 6. For mega. Mega equals times 10 to the 6. This thing. This thing is me scribbling out. All right, so try to use this equation to solve for the other three. If you have questions, let me know. How do you know that 3.8 times 10 to the 8 is meters per second? That is the speed of light, right? Speed of light is 299,798,485 meters per second. I just said it's a lot easier if you just write 3.0 times 10 to the 8, set all those digits. So we'll do a couple more minutes here. By the way, so for A, the equation that I did after all that funny business was just lambda equals C divided by nu. So these two equations are the same thing. I just switched where the variables are. All right, let's start figuring these out. So in B, I give you a frequency. That means we're solving for wavelength. So wavelength equals speed of light, 3.0 times 10 to the 8th meters per second, divided by 1070 kilohertz. Well, kilo equals times 10 to the 3rd. That's what a kilo is. So this is 1070 times 10 to the 3rd hertz, or 1 divided by seconds. The seconds will cancel out here, and our unit will be left in meters. Again, the reason why seconds cancel out is up here. When you have a fraction on your denominator, you can just move it up as long as you switch around the denominator and numerator of your fraction. So you take those two and you divide them together, and you should get 280.4 meters. So that's the wavelength of a AM radio. And if we just compare that to FM, AM is a lot longer, and it's a lot less powerful than FM radio. That's why the signal is worse on AM, but it does travel a lot farther than FM before it loses its energy. So you can actually pick up AM radio from cities far away, and it's all due to the energy of the wavelength and how long they are. That's B. Let's take a look at C. C, I give you a wavelength. So we're solving for frequency. So we can just use the equation as written. Frequency equals speed of light. So 3.0 times 10 to the 8 meters per second, divided by 632.8 nanometers. Here, nano equals times 10 to the minus 9th. Nano is really small. So this is 632.8 times 10 to the minus 9 meters. Our answer here when we do this, meter on the top, meter on the bottom, will be inverse seconds, or 1 divided by seconds, or hertz. So that's good. And when we do this, our answer is 4.741 times 10 to the 14 hertz. So lasers are usually pretty powerful. And if we compared the frequency from a laser to the frequency from radio, the frequency of a laser is much higher. The wavelength is much shorter because they're just much higher energy. And our last one, what is the frequency of an X-ray? So same equation, we're solving for frequency. That equals the speed of light, 3.0 times 10 to the 8 meters per second, divided by the wavelength of our X-ray, 0.052, and it's nanometers. So again, times 10 to the minus 9 meters. Our unit again will be in hertz, and this will be 5.8 times 10 to the 18th hertz. So big number, very high frequency, because it's a very powerful laser. X-rays will chop up your DNA, no problem, because the wave has such high energy. All right, so looking at these, any questions on how to convert between a wavelength and a frequency using the speed of light? How do you determine sig figs? Speed of light is a big number, right? 299,792,485. So that has like 9 sig figs. So I ignore that. And so all the sig figs are coming from these numbers, right? 4 sig figs, probably 4 sig figs. That 0 is ambiguous. So this could be 3 or 4. 4 sig figs, 2 sig figs. Even though we're using 3.0 times 10 to the 8, that's just really a way to save yourself a couple of seconds by just not typing 299,792,485, because the answer is not going to be that different for our purposes, at least. Any other questions? All right, let's move on then. So the last half an hour there, we were just focusing on light being waves. However, light has 2 different properties. They are waves and they are particles. So is it common in the science world, go ahead and type the speed of light like that? Usually, unless you're doing precise calculations. Usually people just do 3.0 times 10 to the 8. If you're in NASA, you probably use all the digits that you can. All right, so light, waves, and particles. And that depends on how you measure it, right? They're either discrete packets of energy or a continuous wave of energy. This comes from Einstein. Basically, what he did is that he shined a light on a piece of metal, and he found that to eject electrons off that metal, you need a certain type of light, a certain energy in that light, which meant that that light energy is not being delivered continuously like you would think in a wave, but it's delivered in discrete packets. You get energy in lump sums instead of just a continuous payment. And he called these packets quanta or photons. And so when we think about energy, like we were talking on the electromagnetic spectrum, it is proportional to its frequency. The higher the frequency, the more energy. And it's also inversely proportional to wavelength, just like the electromagnetic spectrum. And to calculate the energy of a photon, we need a conversion factor. And that conversion factor is Planck's constant, which is given the symbol H. And it has a value of 6.626 times 10 to the minus 34 joules per second. Remember, joules is the energy, SI energy unit. So to find out how much energy a photon of light has, and if you know its frequency, it's this equation. Energy of a photon equals Planck's constant times frequency. Remember, frequency is hertz, or 1 divided by seconds. So when we multiply frequency by Planck's constant, seconds cancel out, and our unit is joules, which is good because that's what we want. We want to know the energy of our light. Here's the other version where we know wavelength instead. So it's Planck's constant times speed of light divided by wavelength, which makes sense because we just said that frequency equals speed of light divided by wavelength. So all I'm doing is I'm substituting my nu, or my v here, for c divided by wavelength. And if we look at the units for this, so Planck's constant is joules times seconds. Speed of light is meters divided by seconds. Wavelength is in meters. And your unit is joules, which is good because we want to calculate energy of photons. So that's the two equations we're going to be using to determine for light, what is the energy of each packet? What is the energy of each quanta? What is the energy of each photon? All of those words are interchangeable there. So, question 3. We have a heat lamp producing 32.8 watts of power. And the wavelength of this light is 6.5 micrometers. How many photons do we emit per second if a watt has the units of 1 joules per second? Right. So I'm gonna take a crack at A for us, and then I'm gonna let you go and do B, because these can be quite complicated when you're first looking at it. A lot of numbers being thrown around, a lot of units. As always, let's draw a little picture. It helps, at least it helps me. So there's our heat lamp. And we have little heat waves coming off of it. Okay, so this, the wavelength of this is 6.5 times 10 to the minus 6 meters, because a micro is times 10 to the minus 6. So that's our wavelength. And we know that this light is producing 32 joules of energy for every second that it's on, because, or 32.8 rather. because it's 32.8 watts, and a watt is a joule per second. So how many photons are emitted per second? That's the question. And a hidden question that's not explicitly listed, but you have to figure out to solve this is, what's the energy of a photon? Because I know how much energy per second this is producing, but I don't actually know what the energy of the photon of this light is. So that's where we need to start. And so we have wavelength. So let's start with this equation that tells me the energy of a photon if I know wavelength. So the energy of a photon equals Planck's constant, 6.626 times 10 to the minus 34, multiplied by the speed of light, 3.0 times 10 to the 8, divided by my wavelength of light, which is 6.5 times 10 to the minus 6 meters. So that's the setup of how to just figure out, what is the energy of one photon? So let me do this calculation. 6.626 times 10 minus 34 multiplied by 3.0 times 10 to the power of 8. Take that number, divide it by 6.5 times 10 to the minus 6. All right, so let me get my pen back out. We have one photon equals 3.058 times 10 to the minus 20 joules. So before I move on to the next point of saying, okay, how many photons is that per second? Any questions about what I've done so far? Any idea how you got 10 times minus 32? The way that usually happens, if you get like 3.058, but you get the wrong times 10 to the whatever, it's usually because you didn't put parentheses in your calculator correctly, or you didn't use parentheses. Because if you put this into your calculator like just as is, it's going to do the first part okay. Then it's going to divide that whole number by 6.5 and then multiply that number by times 10 to the minus 6 instead of dividing it by times 10 to the minus 6. So when I did this just now, I did parenthesis multiplied by parenthesis equals, get that number, then divided by that all in parentheses. That usually helps. So I use the second equation on the page. Yes, because we are given wavelength. So I use the equation that had wavelength in it. Okay, so that's how many photon, or that's one photon, the energy of one photon. So let's go to the second part. How many photons are emitted per second? So my unit for this should be photon per second. And this might seem a little weird, but I can write this number as 3.058 times 10 to the minus 20 joules per photon. And this, to get to this point, it really helps, at least I found it really helps, is to really, when you see units over each other, start saying out loud like what that means. So for 32.8 joules second, what this means is that for every 32.8 joules that the lamp gives off, that takes 1 second at a time. I can also write that as for every 1 second, I get 32.8 joules, right? That's what it means when you have units divided by each other. The most common example that we see in our day-to-day lives is miles per hour. For every 60 miles I go, that takes 1 hour. Or for every 1 hour I travel, that is 60 miles. Right, that's 60 mph, miles per hour. So for here, I said 1 photon is 3.058 times 10 to the minus 20 joules. Well, I can rewrite it like this, where I say 3.058 times 10 to the minus 20 joules is 1 photon, or 1 photon is 3.058 times 10 to the minus 20 joules. Right. So my units can be joules over photons or photons over joules based on what I said up here about that logic. So that part of the problem is probably not obvious. Right. So I want my final unit to be photons per second, because that's what it's asking. Right now, my units are photon per joules. So I need to get rid of this joules on the denominator. So I need to have joules up here in the numerator to do that. And I want to have seconds in the denominator instead. So let's put seconds there. Now, is there any number on here that combines the units of joules and seconds? That would be the watt. So we know that for every 32.8 joules, that takes 1 second of time. Joules cancel out. My unit is photons per second. Do 32.8 divided by 3.058 times 10 to minus 20. When you do that, you find that this lamp is producing 1 point, and the sig fig should be 2 because they're right there, 1.1 times 10 to the 21 photons per second. So just to reiterate, like how I solved that, because I did that like in real time and like without any notes. So I did the process right there and tried to talk it through while you all were listening. But basically, when I try to solve problems, I always try to be aware of, okay, what unit should I end up in? And that depends on the question. How many photons are emitted per second? So my unit should be photon per second. And from there, I knew how much energy the lamp was producing in terms of joules per second. So I already see I have a second here in the denominator. I just need to replace this joules with a photon to get photons per second. And so I work backwards from there to calculate, okay, 1 photon is how many joules then? So that was my thought process. Have my unit here. That's my final unit. Well, I have some information that can give me joules per second. So second on the denominator, that's great. I also have some information here to tell me photons per joule. or joules per photon. So from there, I was kind of able to figure out, okay, I need these pieces of information. Once I have these pieces of information, it's just a big unit conversion problem. And I understand looking at that for the first time and doing these problems for the first time, it's really confusing what you should do when and why you do that. So that's why I'm trying to spell it out explicitly, and also why we have another example problem here. But any questions about A now that I've worked it out here? All right, then let's go on to B. So B should be a little simpler, and I'll give you time to do that. So we'll take like 3 or 4 minutes here, and then I'll come back and solve it. So let me know if you have any questions. All right, so time's running low. So let's take a look at B here. So B, we have a laser that has a wavelength of 532. So laser, crooked laser, wavelength equals 532 nanometers. And the energy of this wavelength is 3.85 millijoules, or 3.85 times 10 to the minus 3 joules. Therefore, how many photons are in the laser pulse? So here we're not dealing with time. It's just a straight, if I shoot it with a laser, how much photons are in that laser? So my unit should be photons here. And again, I have something that's in joules, and this equation will give me joules per photon, or photons per joules rather. So I have a way to convert between the two. So again, the hidden question is just like what we had in 1. What is the energy of a photon for this wavelength of light? So that's what we should be doing first. The energy of a photon equals Planck's constant times the speed of light divided by wavelength, which is 6.626 times 10 to the minus 34, multiplied by 3.0 times 10 to the 8, divided by our wavelength, 3.85 times 10 to the minus, whoops, that's millijoules. That is not wavelength. I'm looking at the wrong number, which is 532 times 10 to the minus 9 meters. So when we get that, we find that the energy of one photon is 3.736 times 10 to the minus 19 joules. And again, we can do the little trick where if we think about speed, right? 1 hour equals 60 miles. And then we can do 60 miles per hour. I can also do that here. One photon is that many joules. So this is 3.736 times 10 to the minus 19 joules, one photon. So this is how much energy I get for one photon. Well, the energy of the entire pulse is 3.85 times 10 to the minus 3 joules. That's what the energy of that laser is. And remember, my units wants to be photons, so I want joules on the bottom, photons on the top. And there's my conversion factor, 3.736 times 10 to the minus 19 joules for every one photon. Take those two numbers, divide them by each other. And this should be 1.03 times 10 to the 16th photons. So a lot of photons in one laser pulse, which makes sense because each individual packet or photon of energy, or photon of light rather, is very low energy. Yet they are all combining to make a pulse of much higher magnitude. So we must have a lot of photons. That should be minus 19, not minus 9. We have a lot of photons that are doing that. All right. So with that worked out, and since we're basically out of time, is there any questions people have about how I did B there? All right, so I know this is complicated stuff, so don't worry if you didn't quite get it at first. Just keep practicing and you'll get there with time. But other than that, I don't have anything left for you. So remember, test 1 Monday. Look in the test, or not, test 3 Monday. Look in the test 3 folder. If you have questions over the weekend, let me know and I'll do my best to get to them. Otherwise, good luck. And hopefully I'll see you Wednesday. So take care, everybody.